All right, I wanted to make a summary of different kinds of stellar explosions that can occur. So these are things that, in some sense, we've talked a little bit about, but I just wanted to kind of pull them all together and make sure that each mechanism is understood. Now, in a type 2 supernova, we have already looked at this kind of a process before, but let's just remind ourselves what it looks like up on the data projector. It's the one on the bottom. So we have hydrogen fusion taking place. Then we have the red giant stage, the iron core. Then you have the iron core collapsing and the rest of the material falling inward. And so that would be just a regular supernova. But there's another variation on this, and that's called the hypernova. Okay? And so what happens here is that if the center of the black hole, the collapsing iron core, is greater than mass that's greater than about 3 times the mass of our sun, then it can continue to collapse until it turns into a black hole. It doesn't turn into a neutron star anymore. It turns into a black hole. And then surrounding that is an event horizon. But then the remaining material can fall inward toward this black hole, and this is a mini version of the supermassive black holes. The infalling matter in the accretion disk, and the stellar-sized black hole, not supermassive, but stellar-sized, has the same basic look to it as the supermassive one did. The infalling matter creates the magnetic field, spiraling inward. And so this kind of a black hole actually doesn't just collapse down quietly. It doesn't go quietly. But instead, the particles are sent spiraling at high velocities along the magnetic poles of this collapsing black hole, and it produces huge directional jets. But this is on a stellar scale now, not on the scale of a quasar. So that's what's called the hypernova. The first one was discovered, the first one that I know about was discovered back in the 1960s. And it was such a powerful blast that the military, the United States military, thought that the Russians had blown off a nuclear weapon in space. And so this created a lot of concern, but then we realized that what had happened is that the Earth was along the line of the greatest intensity of the jet. And so when we started, the mathematicians started figuring out, well, how much energy did this thing have? And they assumed that the energy was shot off equally in all directions. But it wasn't. It was concentrated in these jets. So you have to be aligned with one of these jets to get the full effect from a hypernova explosion. And so that's when they realized that it is possible to generate that much energy from a hypernova explosion as long as the jets are collimated like this. And so if you're out here, you're not going to feel the effects. But if you're in the line of the jet, then you will. And so these are so powerful that if you're anywhere within, say, 50 light years of one of these things, your planet would be destroyed. Your atmosphere would be torn off. 100 light years is still questionable. 1,000 light years, a little safer. So we've dodged some bullets in the past, but it's thought that there may have been some hypernova explosions that have hit the Earth from distances of maybe a couple thousand light years over the history of the evolution of the Earth. Okay, and so this is one kind of supernova that is much more powerful than your regular neutron star type of hypernova. And we don't know whether all black holes blow up like this or not. Maybe some of them go quietly. Some of them may go without generating this kind of a swirling effect with the hypernova explosion. So a lot of this is still being debated and trying to get more data to discover all of the different variations that can happen when a black hole forms. But another type of supernova, so this is number 1 in our list. Number 2 is a type 1 supernova. And so if we look back up at the data projector, that's the one that's on the top. So here we've got a binary star system, and one of the objects is a white dwarf, and the other one, let's say, becomes a red giant. So we have our white dwarf with a mass we know that's less than 1.5 times the mass of our sun, and it's held up by electron forces. Then nearby, let's say we have a red giant star, or some star that has available material to dump down the white dwarf. And then the material starts to build up on the white dwarf and pushes the white dwarf past the 1.5 solar mass limit. At this point then, once the mass it'll explode. And so this is called a type 1 supernova. The kind of explosion that we get here produces more iron and carbon. Than a type 2 supernova explosion. Type 2 supernova explosion we think produces more of the heavy elements. Okay? And this is also called a standard candle because each of these only explodes when the white dwarf gets up to the critical point. And so that means that they're all, we think, have the same brightness. And so this means then that they can be used to measure large distances in the universe, because anytime we see one, we know how bright that it should be. We know how bright it seems to be, so we can tell how far away it is. And so we can then start measuring the distances to other galaxies by looking for type 1 supernova standard candles. Okay, so in reality, the kind of material that forms our solar system we think has to be the right mix of type 1 and type 2 supernova explosion in order to have the right combination of different elements. And this isn't the end of the story either, because we think that there can be neutron star collisions and generally, neutron star collisions result in the formation of a black hole. That neutron stars have so many neutrons that you can form heavier elements, because heavier elements are made mostly with neutrons, maybe 1.5 times as many neutrons as protons in a heavy element like uranium. And so it's thought then that gold, uranium, and other precious metals are produced much more often in this kind of an interaction. And it's thought that something like maybe a thousand years or so before our solar system formed, there was a nearby neutron star collision. And so the reason that we believe that is that it seems like this is the best place to form these kinds of precious elements, and we've got a lot of them on our planet. And so that means that there's also that element to it in getting a planet that has the right mix of all of the different materials that make life as we understand it possible. Is that we have to have enough of all of these different kinds, the remnants from all of these different kinds of explosions in that very rare mix that makes life possible here on the Earth. Another type of supernova, or another type of stellar explosion, I should say, is just the regular nova. Now a nova, as opposed to a type 1 supernova explosion, still has the white dwarf and the nearby red giant, or some other source of material. It doesn't have to be a red giant. Some other source of material. But here in a nova, instead of the material being incorporated into the white dwarf, it superheats on the surface and then goes off like a little pop gun. So this is not of the intensity of a supernova explosion, so we'll call it a smaller explosion. And because this doesn't disrupt the white dwarf, it can keep doing this. You can have thousands of nova explosions from the same white dwarf star. Whereas with a type 1 supernova explosion, the white dwarf is gone after the explosion is over. There's nothing left. We don't think there's any remnant left from a type 1 supernova. So we've got two different kinds of supernova explosions. We've got the hypernova explosion, which is similar to a type 2 supernova explosion, but with the resultant end product being a black hole. We have the neutron star collisions. There are also, of course, black hole collisions that can occur as well. And we also have the nova.